This is Porterville College, Chapter 28, Homework for Physics 104B. Starting with number 15, we have 208 volts root mean square and 400 hertz frequency. What are the peak voltage and the angular frequency? You can find these equations in the book. First of all, for part A, peak voltage is square root of 2 times the root mean square voltage. You should get 294 volts. For part B, the angular frequency is 2 pi times the frequency in hertz. And so when we multiply, we get 2513 radians per second. Number 18, find the RMS current in a 1 microfarad capacitor connected across 120 volt RMS, 60 hertz AC power. Here's the given information. Omega is 2 pi f, so that's going to be 120 pi radians per second. We're going to use from the book, it's equation 28.5. The peak current is the peak voltage over 1 over omega c. Peak voltage is square root of 2 times the root mean square current. Peak voltage is square root of 2 times the root mean square voltage. So we have, since they're both the peak and the RMSs, they're related by the square root of 2, we're going to turn this equation up here. Essentially, we're going to divide through by a factor of square root of 2, and we're left with I RMS equals V RMS over 1 over omega c. So I RMS is V RMS times omega c, and we have omega, we have c, you should get 45.2 milliamperes. Number 19, 470 ohm resistor, a 10 microfarad capacitor, and a 750 millihenry inductor are each connected across 6.3 volt RMS, 60 hertz AC power. Find the RMS current in each. So we're dealing with each of these being separately hooked across. And you can read about those separate sections in section 28.2 in the book. The mathematical relationships for I RMS is V RMS times omega c. For a resistor, it's I RMS equals V RMS divided by resistance. And for an inductor, it's I RMS equals V RMS divided by omega L. So omega in all these cases is 120 pi radians per second. Voltage, RMS, in all these cases is 6.3 volts. And so you multiply by capacitance, or divide by resistance, or divide by omega L. And you should get, for part A, 24 milliamperes, for part B, 13 milliamperes, and for part C, 22 milliamperes. For number 20, find the reactance of a 3.3 microfarad capacitor at various frequencies. Reactance for a capacitor is 1 over omega c. Remember, that's going to be 1 over 2 pi f c. You just plug in those numbers, and for the low frequency of 60 hertz, you get 804 ohms. For the middle frequency of 1000 hertz, you should get 48 ohms. And for the high frequency, you get 2.4 ohms. And you notice, as I wrote here, you can see that a capacitor has its greatest effect, meaning its largest reactance, at a low frequency. Number 23. 50 millihenry inductor is connected across a 10 VRMS AC generator, and a 2 milliampere RMS current flows. What is the generator frequency? we have these relationships. First of all, that peak current is peak voltage over omega L. This translates to RMS current equals VRMS divided by omega L. We're going to solve this for omega to get the frequency. So we get that omega is the VRMS over IRMS L. Plug in those values, 10 volts over 2 milliamperes, 50 millihenries, and you get 10 to the 5th radians per second. We're going to solve for this in hertz, so divide it by 2 pi, and we'll get 16 kilohertz. Number 25 deals with an LC circuit with a given capacitance. It undergoes a period of 2.4 seconds. Find the inductance. We're using this frequency that this equation that the frequency is 1 over square root of LC. Solve it for L for the inductance. L equals 1 over C omega squared, where omega is 2 pi over the period, which is 2.618 radians per second. So we plug that into this formula, and we get the inductance is 8.1 henries. Number 42. Capacitor is connected across a generator whose output is given by the formula. Find the peak current and the magnitude of voltage and current at a specified time, 6.5 milliseconds. Peak voltage is 22 volts. Frequency is 60 hertz, so our formula for time dependence of voltage, V equals 22 sine 120 pi t, where the 120 pi is omega, which is 2 pi times 60 hertz. The peak current is given to us by peak voltage over the capacitor's reactance, which is peak voltage times omega C. 22 volts times 120 pi radians per second times 1.2 times 10 to the negative 6 farads, and you get 10 milliamperes. For part B, what is the voltage at 6.5 milliseconds? We have this formula up here. We're just going to plug in the time. 22 sine of 120 pi times 6.5 times 10 to the negative 3 radians per second. Your calculator must be in radians mode for this to work. And you get 14 volts. For part C, to find the current, use equation 28.4 in the book. You'll notice that the current leads the voltage by pi over 2 radians. On this line, I've written equation 28.4. You can do it either way. You can say current is peak current times sine of omega t plus pi over 2. Or the simpler way, more straightforward, is to say peak current cosine omega t. I've plugged it in using omega t plus pi over 2, although it would be more straightforward to use the cosine version. I use the sine version just to remind us that it looks like the voltage equation, and just to see that there is that relationship that current does lead the voltage by pi over 2 radians. So whichever equation you use, plug the numbers in. Right here on this line, I've abbreviated, because I was running out of space. This says current is 120 pi, which is omega, times capacitance 1.2 times 10 to the negative 6 farads, times peak voltage 22 volts, and then I wrote times sine, all that stuff. And what that means is sine of all of this. You get, see an error right here, excuse me. There we go, milliamperes. You get current is negative 7.67 milliamperes, and here I have it written correctly. The current I'm just taking the absolute value, so the current is 7.7 milliamperes. Number 47. The FM radio band covers the frequency range 88 to 108 millihertz. If the variable capacitor in an FM receiver ranges from 10.9 picofarads to 16.4 picofarads, what inductor should be used to make an LC circuit whose resonant frequency spans the FM band? So it is the inductor and capacitor combination that's going to give us the resonant frequency. And the setup for this problem is that there is a constant inductor, and we have to find out what it is to get those different frequencies for the varying capacitance. So omega is 1 over square root of LC. We want to solve this for L. So L is 1 over omega squared C equals, and then in place of omega, we want this in terms of frequency, cycles per second or hertz. So we'll say omega squared becomes 2 pi f squared. That is going to give us L. So for a constant L, low frequency will be associated with high C. And so when you plug in these values, when you let F1 equals the low frequency, 88 megahertz. That's 88 times 10 to the 6th hertz. You plug it in there, and you should get a capacitance of 16.4 picofarads. Actually, I'm sorry. Let me back up. We're not plugging anything in yet. This is just saying that at a frequency of 88 megahertz, you get a capacitance of 16.4 picofarads. At a frequency of 108 megahertz, you use a capacitance for 10.9 picofarads. Okay, now we're going to plug those values in, either pair of values, either F1 and C1 or F2 and C2. You can do both just to check your work. I've done L equals, and I've plugged in for 88 megahertz, 16.4 picofarads, and what I get is 1.99 times 10 to the negative 7 hertz. You could also plug in for the high frequency, and for the other capacitance and the low capacitance, and you should get that. Number 78. We can model a mechanical system of a mass on a spring using an electric circuit. Suppose a 5 kilogram mass is connected to a spring with spring constant K equals 1.44 kilonewtons per meter. We then model this by an LC circuit using an inductor of 2.5 henries. What should the capacitor be in the LC circuit to have the same resonance frequency? Let's relate things from last semester, a spring with a mass attached. In that case, we had omega equals square root of K over M. We relate it now to LC circuit, being an oscillator. Omega equals 1 over square root of LC. We want the same frequencies, so we'll set them equal to each other. Square root of K over M equals 1 over square root of LC. And we solve for capacitance. When you go through the algebra, you should get that capacitance is mass divided by the inductor divided by the spring stiffness constant. Plug those in, and we get the capacitor that would be useful for modeling the system would be 1.4 millifarads. We can then check our work by assuming that we have the right capacitance, that we've done it correctly. We take this C and the L for the inductor, and we plug it into this equation, and we should get an omega of 17 radians per second. We can also plug it into this equation with the proper K and M and get 17 radians per second. And so for this oscillator, 17 radians per second, and the frequency is 2.7 hertz. And that ends the chapter 28 homework.